Almost every app that touches a database hides this one bug. It can quietly lose real data and report that nothing went wrong. Let me show you in slow motion. 2 support agents, 1 customer, the same refund at the same second. Agent A opens the account. The balance reads $100. She adds a $500 refund and hits save. At that same moment, Agent B opens the same account. He also sees $100. He adds his own $500 refund and hits save. The balance should now read $1,100. You can do the math yourself. 100 plus 500 plus 500. It reads 600. $500 just stopped existing. No error, no warning. Both saves succeeded. The database did exactly what it was told to do. By the end of this video, you will know precisely where that money went, and you will never look at a plain update the same way again. Here is the story we all tell ourselves about databases. You have a row, the customer's balance. It says 100. You run an update, set it to 600, and the database reaches into that row and changes the number. Old value gone, new value in its place. Clean, simple. That story is wrong, and almost every bug where a database quietly loses data begins with believing it. Because Postgres, the database sitting under a huge share of the internet, does not work like that. When you update that balance, it does not touch the row where it lives. Let me show you what it actually does instead. And I promise you, the second you see it, the missing $500 becomes obvious. It starts as one version, balance 100, stamped with a number, the ID of the transaction that created it. Think of it as a birth certificate. Now you update the balance to 600. Here is the surprise. Postgres does not edit that row. It writes a brand new version right next to the old one, 600, with its own birth certificate. Then it goes back to the old version and adds a second stamp, the ID of the transaction that just ended it, a death certificate. The old version is still there, on disk, untouched, simply marked expired. So a row in Postgres is not a value, it is a stack of versions. Every version carries 2 numbers, the transaction that created it and the transaction that killed it, a valid from and a valid until. And because those ranges never overlap, at any single instant, exactly one version is the live one. Delete a row? Same move. Postgres does not remove it. It stamps the death certificate and walks away. The row is still sitting on disk. This is the single most important idea in this entire video, so let me say it plainly. Postgres almost never changes your data in place. It writes new versions and marks old ones dead. There is no undo log, the kind Oracle or MySQL keep off to the side. The old versions just live in your table, right next to the live ones. Which raises a beautiful question. If every version is still lying there, the 100, the 600, all of it, then when you run one simple select, how does Postgres possibly know which version is yours to see? The answer is the idea the whole system is built on, and it is simpler than you would guess. When your query begins, Postgres hands it a snapshot. Now, a snapshot is not a copy of the database. It does not duplicate a single row. It is really just 3 small facts. The oldest transaction still running, the next transaction ID not yet handed out, and the short list of transactions in flight right now. That tiny scrap of information draws a line across time, a cut line. Every version has those 2 stamps, created by and killed by. To decide whether you can see a version, Postgres asks 2 questions. Was it created by a transaction that finished before my cut line? And was it still alive as of my cut line? If both are yes, you see it. If the version was born above your line, then as far as you are concerned, it does not exist yet. So 2 queries running at the very same instant, with cut lines one transaction apart, can look at the same row and correctly see different versions of it. Neither one is wrong. They are simply reading at different points on the timeline. This is called multiversion concurrency control. That is the real name. Multiple versions kept side by side so that concurrency, many things happening at once, just works. And it buys you something close to magic. Readers never block writers, and writers never block readers. A reader looks at an old version while a writer builds a new one. Neither waits for the other. Now, one trap that catches even senior engineers. A version being committed is not the same as a version being visible to you. A transaction that committed 1 millisecond after your cut line is real. It is on disk, it is done. And your query correctly cannot see it. Did it commit? And can I see it? Are two completely different questions. Hold on to that one. It is about to explain everything. Now we can solve it. Rewind to our two agents. Agent A starts her transaction and gets a cut line. She reads the balance, 100. At almost the same moment, Agent B starts his transaction and gets his own cut line a fraction later. He reads the balance too. And because Postgres keeps the old versions and his cut line still sees the world before A's change lands, he also reads 100. Both of them, in their own application code, do the identical thing. Take the 100 they read, add 500, write the result back. Both write 600. A commits, then B commits, and B's 600 is the version that wins. There it is. That is your missing $500. Neither agent did a single thing wrong. Neither one ever saw the other. Each read a true value, then overwrote the other's work. This has a name that is almost too honest about it: the lost update. And here is the part that matters for the code you actually write. This is not a flaw in the update command. If each agent had run one single statement, set balance equals balance plus 500, Postgres would have handled it perfectly. Nothing lost. The bug appears the moment you read a value out into your application, add to it there in Python or Ruby or JavaScript, and write it back. Read, modify, write across two separate trips to the database. That is the pattern that quietly loses money, and it is everywhere. It is the default way an ORM leads you to write. So how do you stop it? You make the cut lines stricter. Postgres gives you levels. The default is called read committed, fast, forgiving, and exactly the setting that let our money evaporate. Under it, if someone changes a row out from under your write, Postgres does not even raise an error. It quietly grabs the newest version, rechecks your condition against it, and if it still matches, proceeds. If it no longer matches, it silently skips that row. Turn the dial up one notch to a level called Repeatable Read, and the behavior changes completely. Now, when two transactions collide on the same row, Postgres refuses to guess. It aborts one of them with a serialization error and hands your application a plain instruction. Start over with a fresh cut line. Your code has to catch that error and retry the whole transaction. Postgres will not retry for you. And there is one more attacker even that does not catch. Two transactions read the same rows, then each one updates a different row. Nothing collides, both commit, and together they break a rule that neither one broke alone. Picture two doctors, each checking that at least one of them is still on call, each clocking off at the same instant, and now the hospital has nobody. That is called write skew, and catching it is the entire reason the strictest level, serializable, exists. It does not lock everything and run transactions one at a time. That is the myth. It quietly watches for these dangerous patterns and cancels one transaction the moment it spots one. Every trick has a bill, and Postgres runs the whole tab in one place. Go back to that stack of versions. Every time you update a row, the old version stays behind, marked dead. Update a row 1,000 times and you have one live version sitting on top of 1,000 corpses. That pile is called bloat. And something has to clear it. That janitor is a process called vacuum. Now, 3 things about vacuum surprise almost everyone. First, delete 1,000,000 rows from a table, run an ordinary vacuum, and the table does not get smaller on disk. The file stays exactly as large as it was. Vacuum marks that space reusable inside the table, but it does not hand it back to the operating system. To truly shrink the file, you have to rewrite the entire table. Second, a plain read-only select can write to disk. The first query to read a row after its transaction has settled stamps a little committed hint onto the page to save the next reader the effort. A read quietly causing a write. On the newest Postgres, that can even reach the transaction log. And third, the one that takes production systems down. Vacuum can only remove a dead version once no running transaction could still possibly need it. So one old transaction, left open, holding its cut line, freezes cleanup across your entire database. Not just its own table, every table. I've watched this happen. A client running Odoo, which is Postgres underneath, a reporting job opened one transaction at the start of the business day and held it open for hours. For that whole stretch, Vacuum could not remove a single dead row anywhere in the database. Their busiest tables, the ones churning through updates all day long, swelled. Queries that used to take 40 milliseconds crawled to 40 seconds. One connection sitting perfectly still, quietly starving the entire system. The fix was almost insulting in its simplicity. End that one transaction. The bloat drained and the database exhaled. And there's a countdown running underneath all of it. Transaction IDs are numbered on a circle, and every table has to be frozen at least once every 2 billion transactions, or its oldest rows would suddenly look like they came from the future. Freezing is another job Vacuum does, stamping old rows as permanently visible so their ancient IDs stop mattering. Let Vacuum fall far enough behind and Postgres does something that looks drastic but is actually protecting you. It stops handing out new transaction IDs. Not a crash. Reads keep serving. Vacuum keeps running. Only new writes are refused until the cleanup catches up, because the alternative is losing your data. Companies you have heard of have eaten hours of downtime learning exactly that. So, 2 people clicked save and $500 vanished. Not because Postgres failed, because it did precisely what it promised. It kept every version. It handed each transaction its own consistent view of the world, and it let neither one block the other. The money never disappeared. 2 true views of reality simply disagreed, and one of them wrote over the other. Everything you just watched, the stack of versions, the cut line, the dead rows, the janitor, the countdown, all of it falls out of one decision. Postgres never changes your data in place. It writes a new version and marks the old one dead. Sit with that single sentence and half of Postgres stops being mysterious. And this one row, with its little stack of versions, is a single cell in a much larger machine. There is a log that survives a power cut, indexes that can make a query slower, not faster, a planner that quietly overrules the instructions you thought you gave it. But those are other corners of the map. We will get to them.